So I think we can start with the topics of Gauss law. This is from what we have learned last Thursday. So we just continue with the topics of Gauss law now. All right. So this is what we have learned from our class last Thursday, the Gauss law, in which we start with the flux electric flux, the concept of electric flux, and then we proceed with the concept of electric flux density. And from that onwards, we have formulated the equation of Gauss law. So this is the equations, which is the closed surface integration of d dot ds equals to enclosed charge. Okay, and we did this example in which we have applied the Gauss law in calculating the electric flux density D and subsequently the electric field intensity E due to a point charge. Yeah. So these are the steps that have been taught last Thursday. So we have three steps. If we can recall back, the first step is to draw a closed imaginary surface, or it can be, in short, we call it just a Gaussian surface. Yeah. Number two is we apply the Gauss law to find the D, and subsequently we apply these equations which relates the flux D and also the field intensity E, in which we can further obtain the E field vector. Right, so these are the steps that have been applied in calculating the E field based on the applications of Gauss law. And we have verified that the equations obtained, the E field equations obtained from the Gauss law is actually same with the equations of E field from the Coulomb's law. Yeah, so this is what we have done last week. So now we're going to proceed with the usage of Gauss law, application of Gauss law in calculating the E field intensity due to a line charge structure. Okay, so there is a special treatment for the case of line charge density, in which the Gauss law can only be applied for the case of infinite length of line charge. Yeah, infinite length of line charge, which means that the Gauss law cannot be applied for the case of finite length of line charge. Yeah, so this is based on what we have learned in our lecture number 4 before, in which we have learned that there are two methods, two ways of calculating the E field intensity for the case of line charge, in which we have a case of infinite length, yeah, and then we have infinite length of line charge, yeah, in which we have learned that the Coulomb's law can be applied in calculating both conditions. But for the case of Gauss law, as I did mention here, it can only be applied for the case of infinite length of line charge, due to the case of this Gauss law can only be applied for a symmetrical charge distribution only. Yeah, symmetrical charge distributions only. So looking at this particular infinite length of line charge, yeah, when we have infinite length, yeah, this is our rho L. Okay, so we can see that this particular charge structure, which is infinite in length, is called as symmetrical. Yeah, it's called a symmetrical charge. In comparison with the finite length, yeah, for instance, we have this particular finite length, rho L, in which the length is only from A to B. Yes, a finite length. So we cannot say that this particular line charge is symmetric. Yeah. All right. So this is called asymmetrical. Yeah, asymmetrical. So asymmetrical charge distribution. Yeah. Okay. So for that particular case, this finite length of line charge cannot be, the Gauss law cannot be used to find the E field due to the finite length of line charge. So it can only be applied for the case of infinite length of line charge. Yeah. So that's the things that you have to understand. Yeah, the limitation of Gauss law. Yeah, as compared to the Coulomb's law that we have learned before. Okay. So let us proceed now with this calculation of E field intensity for the case of infinite length of line charge. So for instance, if you want to find the E field due to this infinite length of line charge, let's say at this particular point, Okay, so we have a distance here, a point here, where the distance is r. This is called a perpendicular distance. Yeah, right. So from we have learned previously in Coulomb's law that the E field for the case of infinite length of line charge will be rho L over 2 pi epsilon of r direction of r. Okay, so this is the equations that we have seen or we have learned before. Okay, so we're going to prove that by applying the Gauss law, we can obtain the similar equations as this. Okay, so for that, let us proceed with the Gauss law now. So there are 3 steps that need to be taken. The first step is this one. Okay. So the first step is to draw a closed imaginary surface. Okay, draw a closed imaginary surface with radius of r. Yeah, radius of r, in which this closed imaginary surface, or we call this as a Gaussian surface. Okay, it must enclose this particular point, or it must pass through this point of interest. Okay, so for a case of infinite length of line charge, you have to choose appropriate Gaussian surface. So in this particular case, your appropriate surface to be used is a cylindrical surface. Yeah, cylindrical surface, right? So remember from the case of point charges before, your Gaussian surface is a spherical surface. Okay, but for this particular case of line charge, your Gaussian surface is a cylindrical surface. Yeah, so you're going to have to draw a cylindrical surface. So that should be the case where we assume that your Gaussian surface or your closed surface here is having a radius of r, yeah, which is having a similar radius with this particular point, and the height of this Gaussian surface is L. Okay, so that should be the first step, which is to draw a Gaussian surface. Okay, number 2, step 2 is to apply the Gauss law, in which subsequently we can find the flux density D, in which by applying the Gauss law, we have the equations where we have D dot ds, okay, shall be equals to the enclosed charge. Okay, so as what we have learned last time, this d dot ds is the integration on the closed surface, while the enclosed charge here is the charge inside the surface, yeah? Inside the surface. Right, so let us proceed with left-hand side first, yeah? Left-hand side, which is the d dot ds closed surface integration. Okay, this is the one. So we can see that based on this closed surface, we are supposed to have 3 different surfaces. The first one is considered to be the top surface. Secondly is the bottom surface. And thirdly is your curved surface. Yeah, so we have 3 surfaces that build up this particular closed surface structure or Gaussian surface structure. So this integration supposedly shall be now divided into 3 different integration, which is we have to integrate with respect to surface number 1, and then we have to integrate with respect to surface number 2, and also integration with respect to surface number 3, because these three surfaces are the surfaces that build up the closed surface integration. So we can have this as equals to close integration of d dot ds for a surface number 1 plus integrations of d dot ds for a surface number 2 and d dot ds for your surface number 3. So we have 3 surfaces there. Okay. Right. So now let us evaluate this integration one by one. Right. For the first surface, we know that for this particular top surface, your ds is here. I have to use a red color, a red marker then. Okay, that is your ds for the first surface. Yeah, that should be the vector of ds, in which from what we have learned previously, yeah, we can write this as equals to r dr d phi, and the direction for the surface vector here will be direction of z. If we take that this is z direction, that is your x direction, and that should be the y direction. Yeah, so we have z direction for the top surface. Similarly, for the bottom surface, your ds for the bottom surface should be equals to r dr d phi, and also the direction will be negative of z direction. Whereas for the curved surface, the top surface here, your ds vector shall be equals to r d phi dz, and the direction for the surface vector here will be direction of positive of r. Okay, right, yeah, so hopefully you understand regarding this ds then. Okay, for the top surface, for the surface number 1, we have obtained the ds for all the surface here, yeah, surface number 1, 2 and 3. So now we have to obtain or understand what should be the vector d for surface number 1, surface number 2, and surface number 3. Okay, for surface number 1, we can see that based on this infinite length of line charge, and from what we have learned before, that the flux directed from this infinite length of surface charge, line charge, will be in the direction of r. Okay, remember that we have learned this previously, yeah? So the direction of your flux is in the r direction for this infinite length of line charge because it follows the direction of the E field. Okay, so for that particular case, we have learned also that the flux density D and the electric field E is having same direction. So due to that, we can see that for this particular case of infinite length of line charge, your vector D should be in the direction of R only. Yeah, so we can see that now for this integration for surface number 1, we are going to have D vector as dr direction of R. Your ds, I just put it as direction of Z, plus for the second surface, going to have dr direction of R also, and the ds will be ds direction of negative Z, plus for the third surface, which is the curved surface there, we have integration of dr direction of R dot ds, which is r d phi dz direction of R. Okay then. Okay, please ask any questions if you have any ambiguities regarding the solutions. Okay, so let us proceed now with the dot product for each surface 1, 2, and 3. For surface number 1, since we have a dot product between different vector, r and z, so this dot product will give us 0. Similarly, for surface number 2, we have a dot product with a different vector, r and negative z. This will also be 0. But for the third surface, yeah, the third surface, which is the curved surface, we have dr direction of r, and the ds is r d phi dz direction of r, in which we're going to have a similar dot product of, a dot product with a similar unit vector. So we can have that the d dot ds integration will be only contributed, yeah, by the third surface. Yeah, we're going to have it as dr, and if we further integrate this, we are going to have it as equals to 2 pi r of L. Okay, because your height of your closed surface is L, and when you integrate the phi, you're going to have 2 pi RL. So that should be the answer for the left-hand side integration for the dot ds closed surface integration. Okay, any question for this before we proceed further? No? Okay, let us proceed with the right-hand side integration. Okay, so for right-hand side integration, which is the enclosed charge, so right-hand side, we are going to have that the enclosed charge is a charge inside the Gaussian surface. Okay, so based on this diagram, can I ask Sharik Faisal? Sharik Faisal, are you in my class now?
Yes, Professor.
Okay, can you please help me? Can you identify what is the enclosed charge here for this particular case?
Is it the one in between the cylinder?
Correct, which is covered by the cylinder. So what is the equation, the term that can be used in for the for the enclosed charge here?
So we will be integrating with the boundaries being, I suppose, the radio and the surface at top.
No, because the enclosed charge is a charge enclosed by the Gaussian here. What is the charge? Enclosed by this closed surface. Okay, never mind. Thank you very much, Sharik, for your response. Okay, we have that this length, this line charge is having a density of rho L, coulombs per meter, right? And we have the length which is bounded by the Gaussian surface is given by L, which is in meters supposedly. So if we want to find the enclosed charge by the Gaussian or by the closed surface here, simply we just multiply the rho L and L. Am I right? Because rho L is in coulombs per meter and your length of the closed surface is L. So if we multiply these two terms here, the rho L and L, so we're going to have the amount of charge inside this Gaussian surface. Am I right? So we're going to have the enclosed charge will be simply rho L multiplied with L. That should be your enclosed charge. Okay? All right. So hopefully you understand. So based on this, you have obtained the equations for the left-hand side and also the equation for the right-hand side. So we just equate both of them. I'm going to use this space up here at the top. So we're going to have that the right-hand side shall be equal to the left-hand side. Okay, so we're going to have that dr of 2 pi rl. This is subscript of r, yeah, sorry, d subscript of r, yeah, shall be equals to rho L of L. So L can be cancelled out. So we're going to have that the dr shall be equals to rho L over 2 pi of r. So that should be your dr. Yeah, that should be your dr, which is the magnitude of the d component. Yeah, for the component of r, yeah, for the d. So from here we have agreed that the vector d for this particular case of line charge density, the d will only be in the r direction. Yeah, because the component of theta and the component of phi, sorry, the component of phi, sorry, phi and the component of z, both of them equals to 0 because there is no flux in the direction of phi and z. Yeah, as I mentioned earlier. So due to this, your vector d for the case of line charge structure or infinite length of line charge will only be contributed by the r component. We're going to have the d as dr direction of r. Yeah. So from this, we can write that the vector d will be dr direction of r, and subsequently, knowing that dr is rho L over 2 pi r, we're going to have rho L over 2 pi r direction of r in coulombs per meter squared. Okay, so we have obtained now the flux density D. So this flux density D basically is the flux density which is measured or calculated here. Yeah, which is on the surface of your Gaussian, on the curved surface of the Gaussian. Okay, this is the flux density D that we have calculated. Yeah, I repeat again, the flux density D here is the flux density which has been calculated on this particular curved surface, yeah, which is having a radius of r. So from here, we can find that from equations of d equals to epsilon naught of E field, which is supposedly to be a third step, yeah, that should be the third step, yeah, which is to use this equation to find the E field. We can just write that the E field based on this equation, our E field will be equals to the vector d over epsilon naught, which will be rho L over 2 pi epsilon naught of r direction of r in volt per meter unit, in which this E field intensity, E field, is measured at any point on the curved surface. Yeah, at any point on the curved surface here, yeah, whether here, as long as the distance for that particular point from the line charge is r, where r is your perpendicular distance from the line charge. Okay, so we have obtained this equation, which is somehow similar to the Coulomb's law equations that we have seen earlier in chapter 2 before. Okay then, is there any questions related to these method of Gauss law used in calculating the E field for the case of infinite length of line charge. Okay, so I just want to remind you that the Gauss law cannot be used for the case of finite length of line charge. So if you are facing a problems of finite length of line charge, so you have to go back to the Coulomb's law. Yeah, the Gauss law can only be used for the case of infinite length of line charge. Yeah, so please be reminded on this. Okay, any more questions? Any questions related to this slide on the Gauss law? Okay, if there's no question, let us proceed with these slides then, which is on Gaussian surface, the characteristics of Gaussian surface. So these are the characteristics of Gaussian surface that need to be understood. Okay, number one, your Gaussian surface must be a closed surface structure. It's very important, yeah? The Gaussian surface must be a closed surface structure. And from two examples that we did before, for the case of point charge, for the case of line charge, we have used a closed spherical surface for a point charge and a closed cylindrical surface for a line charge. Okay, so your structure or your Gaussian surface must be a closed surface, number one. Number two, the surface must be symmetrical. Must be symmetrical. What is meant by symmetrical? Okay, remember, when we use a Gaussian surface for the case of point charge, yeah, we have a point charge Q and we have a spherical surface which is to bound this particular charge. So this spherical surface is a symmetrical surface, yeah? Yeah, it is a symmetrical surface. Okay. Similarly, for the case of line charge that we just recently did, yeah, we have infinite length of line charge. Then we draw a cylindrical surface. So this cylindrical surface is also symmetrical. Okay, so your Gaussian surface must be symmetrical. Yeah, so that should be the second characteristics of Gaussian surface. And number three, the flux must be directed either normal or parallel with the surface. So it's very important, yeah? Okay, let us have a look at this particular example then. For your point charge here, we know that the point charge, the flux directed will be in radial directions, right? So that should be the direction of flux, yeah? The flux direction is here. So it can be said that the flux is said to be directed normal with regard to this particular spherical surface. So it follows these characteristics in which the flux is whether normal or parallel with the surface, yeah? Okay. And for the case of this cylindrical surface, the flux is in the radial direction. So that's your flux direction, yeah? So it can be said that the flux is also directed normal, which is normal with regard to this curved surface, and parallel with regard to this particular top and the bottom surface. So this cylindrical surface is also fulfill the third characteristics in which the flux must be normal or parallel with the surface. Okay, yeah? So these are three characteristics of Gaussian surface that need to be taken in consideration when we want to use it in applying or in solving the problems related to the Gauss law. Okay, so these will be a common problems that you are going to face in electromagnetics problems, yeah, where we're going to have maybe a point charge problems, infinite length of line charge problems. We're going to have a problem of sphere, uniform rho s, sphere of uniform rho v, cylindrical structure of uniform rho s, and cylindrical structure of uniform rho v. So for this particular case of structures, these are the respective Gaussian surface that shall be applied. Yeah. So for the point charge, we need to adopt a spherical surface which has been used before. For the case of infinite length of line charge, also you need to use a cylindrical surface. Yeah. For the case of sphere, you have to adopt a spherical surface as a Gaussian. Similarly, for the case of sphere of uniform rho v, you also need to adopt a spherical surface as a Gaussian. And for for this cylindrical structure of uniform rho S and uniform rho V, your Gaussian surface used must be a cylindrical surface. Yeah. So it's either spherical or Gaussian surface. So it's either spherical or cylindrical structure to be used as your Gaussian surface. Yeah. Right. So these are the common problems and the respective Gaussian surface that need to be used in solving the problems. Yeah. Okay. All right. This is for the third case where we are having a surface charge structure. Yeah, a surface charge structure. And I did mention here that the Gauss law can only be applied for the case of special case of surface charge, which will be or which must be infinite area of surface charge. Yeah? Infinite area of a surface charge. So if you are having a finite area, yeah, finite area, for instance, for what we did in our previous chapter 2, for instance, if you have a circular structure having a radius of A, we have a rho S charge on this particular surface. So this is considered to be finite area, yeah, not infinite. So for this particular case of surface charge distribution, we cannot use the Gauss law. Yeah, we cannot use the Gauss law. So for this particular case, you have to use the Coulomb's law in calculating its E field intensity. Okay, so the Gauss law can only be applied for the case of infinite area of a surface charge. So you have to be, you need to understand this clearly. Yeah. Okay, so let us proceed with this case where we assume that this surface that we have here is infinite in area, Okay, for example, if you want to find the electric field somewhere here, which is having a height of A, yeah, a height of A from your surface, yeah, from your surface charge, where the surface charge is having a density of rho S coulombs per meter squared. Okay, so if you want to use the Gauss law to find the E field at this particular point of A, so you have to adopt the Gaussian surface. Number one, you have to draw the Gaussian surface in which the Gaussian surface must pass through this point of interest of A. Okay, you must pass through this point of A. So in this particular case, you have to adopt a cylindrical surface. Yeah, cylindrical surface as a Gaussian surface. So your Gaussian surface should look like this. Okay, in which the Gaussian is having a radius of R. Yeah, radius of R, and the height is A, in which the top surface here must pass through that particular point of A. Yeah, that point of A. Okay, so that should be your Gaussian surface that need to be used. Number two, you have to apply the Gauss law, and subsequently you must be able to obtain a flux density D. Okay, so let's have a look at the Gauss law calculation for these problems. Okay, so we have the d dot ds equals to the enclosed charge. So this is the equation from the Gauss law. Okay, we assume that this particular surface, I mean the Gaussian surface here, this cylindrical structure, the cross section of it, let's say, is having a area of delta S, for instance. Yeah, I mean this, but the cross section of your cylindrical structure is having a surface area of delta S. Okay, so for this, we can write that the left-hand side integration can be calculated as d dot ds for a surface number 1 plus d dot ds for a surface number 2 and d dot ds for a surface number 3. So we have, this is surface number 1. Down here, we have a surface number 2, and here we have a surface number 3. Okay, yeah? And the enclosed charge, I can just write this here as, sorry, this is ds, yeah? And the enclosed charge is simply written as rho s ds integration. Okay, so for left-hand side, for surface number 1, we can write that the flux density D, yeah, dot product with the ds. So For surface number 1, what should be your surface vector then? It should be a ds magnitude. Yeah, magnitude. And what should be the direction of unit vector for surface number 1? Fadila Rahmat, are you in?
Yes, tutor.
Okay, so what should be the direction of unit vector for surface number 1?
Z.
Thank you very much. Very good. Okay. And for surface number 2, what should be the direction of unit vector for surface number 2?
Negative Z.
Thank you very much. Very good. So we're going to have that for the surface number 2, the ds will be ds in the direction of negative z. And for the surface number 3, it should be ds vector should be ds direction of r. Yeah. All right. Good. Thank you very much, Fadila Rahmat, for your answer and for your response. Very good. Okay. Then we have for surface number 1. We know that for this particular case of flux, for this particular case of surface charge density, your flux will be directed normal with regard to the surface. Yeah, it means that for surface number 1, your flux density D can be written simply as dz, the direction of positive z. Yeah, because we can say that for this particular case of surface charge with infinite area, your flux direction is only normal with regard to the surface. So for the top surface, your flux density should be dz direction of z, whereas for the bottom surface here, your flux d vector should be dz direction of negative z, because the direction of the flux is normal with regard to the surface. Am I right? Yeah? Okay, so we can just write that for this particular equation, for surface number 1, we are going to have a dz, and the ds integration, when you integrate the ds, you're going to have a delta s direction of positive z, because as I mentioned before, the integration for this ds will give us the delta s, which is the cross section of the area. So that's why we have a delta s here simply. And for surface number 2, we're going to have dz direction of negative z, and the ds vector down here should be, when we integrate it, we're going to have a delta s direction of negative z. And for the third surface here, since the direction of your ds is positive r, but knowing that the flux direction is negative or positive z, so we are going to have two unit vectors which are perpendicular with each other. So due to that, for surface number 3, the dot product will be 0, because as I mentioned before, the d is in the z or negative z, but the ds in the r direction. So dot product will give us 0. Yeah. So we have 0 for that third integration, and for the right hand side integration, the rho s ds integration, which is the charge enclosed by the Gaussian. Yeah. Sorry. Okay, this is the one. The charge enclosed by the Gaussian. We know that the charge density is rho s coulombs per meter squared. The cross section is the delta s. So simply the charge enclosed should be rho s multiplied with delta s. Yeah. So that should be the charge enclosed by the Gaussian. So we're going to have a rho s of delta s. So we proceed, going to have 2 dz of delta s equals to rho s delta s. So delta s can be cancelled out. So we're going to have rho s shall be equals to, sorry. We're going to have here the ds shall be equals to rho s divided by 2. Not ds, it should be dz. I apologize. Yeah, it should be dz. Okay, so that should be the flux density, which is calculated here on this particular surface. Okay, so I can write here that the dz calculated here should be equals to rho s over 2, and the dz calculated down here should be similar, which is rho s divided by 2. That should be the magnitude of the flux density measured on this surface of number 1 and surface number 2. Okay, and knowing that from our discussion before, the flux density will be dz of z or dz of negative z, yeah, depending on the locations of your point. So from here, we can just write for the top surface, your d vector will be dz of z positive, which will be rho s over 2, direction of z. And for the bottom surface here, your vector d will be dz, direction of negative z, because the flux will be pointing downward. So we're going to have it as rho s over 2, direction of negative z. Okay, and from these two results, we can agree that the flux density d by right should be rho s over 2, direction of normal, in which normal will be based on the position of the point, whether it is on the top surface or on the bottom surface of your charge distribution. Yeah, and from your obtained d, you can use the equations of d equals to epsilon of e. Yeah, where we have d equals to epsilon of e. So we're going to have the E field will be d over epsilon naught, which will be rho s over 2 epsilon naught in normal direction. So I believe that we have seen this equation before, right? So this is the equation for the E field produced by infinite area of surface charge. And by using the Gauss law, we have successfully produced the same equations as before. Okay, any question for this case of Gauss law, for the case of infinite surface charge distribution?
Doctor,
Yeah,
may I know why there is the 0 for the surface 3 closed surface integration?
All right, thank you for the questions. Okay, for the surface number 3, can you please help me, Wei Han? What is the vector ds for surface number 3? Okay, we just have a ds then. What should be the direction of the vectors then? This is the direction for surface number 3.
What is the ds? The
Okay, ds is a magnitude, the magnitude, yeah. So it should be basically it should be r dphi dz. Okay, never mind about that. I just want to know what's the direction for your vector for the ds. It should be r. Am I right? Because surface 3 is your curved surface, right? It's your curved surface. Am I right?
Yes.
Yeah. So you go back to this structure. So surface 3, is it surface number 1, surface number 2, or surface number 3? This is based on our discussion in correct. Surface number 3. So surface number 3, what is the unit vector for the surface vector then? Should be r. Am I right?
Yes.
Yeah. Okay. So knowing that, for your flux produced by this infinite area of surface charge, the flux is whether normal upward or normal downward. Am I right? For the case of infinite area of surface charge. Agreed, Wei Han?
Yes.
Okay, so dot product between this vector, which is perpendicular, and the ds, which is parallel, is it 0? For the third surface?
That means the dot product will be 0, is it?
Correct.
Okay, I know. I understand.
Okay, understood, yeah? Okay, thank you. Welcome. Okay, yeah? So hopefully you understand clearly about these issues. Thank you very much for the questions. Okay, let us proceed with this exercise number 1, which is produced or obtained from Skytech book. We are given a case of a sphere, R0 radius, and uniform rho v, coulomb per meter cube distribution. So if you can sketch the diagram, you're going to have like this. Okay, that is our charge, having a radius of R0, and the density of charge is rho v coulombs per meter cube. So this is a volume charge. It's a volume charge distribution, which means that the charges are accumulated all the spaces. Yeah, accumulated or fill in all the spaces inside this particular sphere structure. So the question is, find the expression for the d and the e inside and outside of this particular sphere. Okay, yeah. So I repeat again, the charges are everywhere inside this sphere. No charge elsewhere, only inside the charge, yeah? Inside this spherical charge. So we have two conditions, two things to be obtained, which is to find the D and E for two regions. The first region is inside the sphere, and second region is outside the sphere. So let's find out the D and E for a region inside the sphere, which is R less than R naught. R is a variable. Yeah, R is a variable which is a radius of R less than R naught. Or it can be said that this is a region inside your sphere. Inside your sphere, yeah? Inside your sphere. Okay, so you have, in this particular case, yeah, since we have a spherical charge distribution, okay, you have to adopt either the Coulomb's law or Gauss law in solving the problems. So when you are facing a problems related to the spherical structure, yeah, related to spherical structure, always opt for Gauss law. Yeah, always opt for Gauss law. Always go for Gauss law when you are facing a problems of spherical charge distribution. Okay, so for that, we are now ready to use a Gauss law for the case of these problems. Yeah, so the first case is for R less than R naught, which is inside the sphere. So number one, step one, you have to draw a Gaussian surface. So what's the Gaussian surface for the spherical charge distribution? So as what we have done before, the appropriate Gaussian surface to be used will be a spherical also. So that should be your Gaussian surface, which is a spherical surface, a closed spherical surface. So the red marker here, or the red colored here, is your Gaussian surface, yeah? And the Gaussian surface is having the radius of R, which is representing this R. Any point, any radius inside this sphere is R, because R is a variable, yeah? You have to notice this. Okay, so you have to choose the Gaussian surface. That's the first step. You have done it. Very good. Second step is that you have to use the Gauss law. The d dot ds equals to enclosed charge. Okay, so d dot ds here is the charge, is the integration on the Gaussian surface. Yeah, that's a Gaussian surface. The enclosed charge here is the charge inside the Gaussian. Okay, so you have to know this, yeah. That should be the left-hand side, which is the integration on the Gaussian surface. The Q enclosed is the charge inside the Gaussian. So let us proceed with the integrations, and let us proceed with the Gauss law first. So for left-hand side, we have closed surface integration of d dot ds. Okay. Lau Deng Jian, are you in my class?
Yes, doctor.
Okay, please help me. For the d vector, what should be the vector d that shall be used in these particular problems? We have the d will be r direction. We're going to have a theta direction, and we can have a phi direction because we are using a spherical coordinate system. But looking at these problems, you have to choose only one, whether it's r, theta, or phi. So which one will be your selection then?
R.
Good. The reason for that?
Because
Okay, thank you very much, Ding Jian, for your effort. The reason for that is that we assume that a spherical charge basically is said to be evolved from a point charge, yeah, a point charge. So the point charge, if we increase the radius, it really becomes a volume charge. Am I right? A spherical volume charge. So due to this particular argument, we can say that the volume charge, for a case of spherical structure, will be having a direction of r, which is similar to the direction of E field for the case of point charge. Yeah. So thank you, Deng Jian, for your response. So the theta and the phi direction can be ignored. We can only have an r direction for the vector d. So we're going to have D as a dr direction of R, and the ds, yeah, ds is the integration on the Gaussian, yeah, on this particular red colored surface. So what should be the ds here on this particular surface? Quek Chen Pen.
Yes, doctor.
Yes, what should be the ds to be used here, Chen Pen?
R dv dr d theta.
Okay, it should be r squared sine theta dr, sorry, r sine squared, okay, r squared sine theta d theta d phi. Direction of? The direction of the ds, Chen Pen?
The direction of R.
Thank you very much. Always go back to this rectangular structure. Okay, so the ds should be surface number 3, right, Chen Pen?
Yes.
Yeah, so it should be direction of positive r, yeah? Oh, your cat is it your cat? Okay, thank you, Chen Pen. Thank you very much, yeah? Okay, so that should be the ds to be used, yeah, for your case. So you're going to have the ds should be r squared sine theta d theta d phi, direction of r. Thank you for your response. Okay, so we have done with the left-hand side. We can proceed with the integration straight away. We're going to have dr, and we integrate this one. We're going to have 4 pi r squared, which is the surface area for this particular Gaussian surface with the red colored surface. We'll be having area of 4 pi r squared, yeah, because the radius of it is r. Remember, r is a variable. R is a variable which is any point, any radius less than r naught, or any point inside the radius or inside the sphere structure, yeah. So you have to remember that. Okay, the right hand side will be the enclosed charge, yeah. The right hand side now will be the enclosed charge, the Q enclosed, the charge inside the Gaussian, yeah. So it should be integration of rho s ds, I believe. So straight away we can have it as rho s of 4 pi r squared. Sorry, not rho, my apologize, sorry for that. My apologize, my mistake for this. My apologize, sorry. Sorry for that. Not rho s ds. It should be rho v dv, yeah? Rho v dv, because your charge is a volume charge. Sorry for this. Okay, so volume charge. So you're going to have that the rho v is given. The dv will be based on the dv for your spherical structure, which is r squared sine theta dr d theta d phi, and subsequently you're going to have it as rho v 4/3 pi r power of 3. Okay, so that should be your enclosed charge, which is the charge inside the Gaussian, yeah, inside this red colored structure. So we can equate left and right. So we can equate left hand side and right hand side. So we're going to have dr 4 pi r squared will be rho v 4/3 pi r power of 3. So cancel out the 4 pi, cancel out the r. We're going to have dr equals to rho v r divided by 3. Okay, and from our discussion before, we have agreed that the d will only be in r direction. So we can just write from here that the vector d will be dr direction of r, which will be rho v r divided by 3 direction of r. Okay, so that should be your flux density d, which is calculated here on the surface of r. Yeah, that should be your flux density d, in which r is a variable, and this equation of d is valid only for any point, any radius inside the r naught or these conditions. Yeah, this is the valid point of r. Yeah, as long as it is less than r naught. Okay, so now we have obtained the vector d successfully. So the third step is what? The third step is to find the E field, which is based on the equation of d of epsilon of E. So from what we have obtained here, the d, we can straight away find the E field, which is rho v over 3 epsilon naught of r, direction of r in volt per meter. So just now it is in coulombs per meter squared unit, yeah? So the E field has been obtained now, which is rho VR over 3 epsilon naught direction of R volt per meter. Okay, any questions for this? Okay, so we have obtained only for the position, the first case, yeah, which is any point inside the sphere structure. Okay, the second step or the second task to be done is to find the D and E outside the sphere. So for the case inside the sphere, is there any question? No, yeah? So if there's no questions, let us proceed with the second part, which is to find the D and E inside the sphere, so outside the sphere. Look at that. Okay, so for the second task, right? So this is your sphere. This is your radius of R naught. The charge is rho V. Yeah. So outside the sphere, which is outside, you're going to use R bigger than R naught. Okay. So again, R is a variable, but this time R is any point bigger than R naught. Yeah. So you have to draw the Gaussian surface. Step number 1. Yeah, draw the Gaussian surface. So when we draw the Gaussian surface, your surface should be somehow located outside here. That should be the R, which is similar to this. Yeah, we have to represent this R as this, which is any point bigger than R naught. Yeah. Okay, done. Your Gaussian surface will be a spherical also, a spherical, but this time your sphere structure is having a radius of R which is bigger than R naught. Yeah. Okay, step number 2. Step number 2 is that you have to use the Gauss law to find the D. Yeah, the D dot ds equals to the enclosed charge. And as what we have agreed before, the D dot ds is calculated on the Gaussian surface, on the red colored surface, while the enclosed charge here is the charge inside your Gaussian surface. Yeah, you have to remember that, yeah? The D dot ds integration is on the surface, and enclosed charge is the charge inside the surface. So let us proceed the left-hand side. Okay, the D dot ds integration, enclosed surface, which is measured here on this particular surface. So as before, the vector D will only be in the R direction. Yeah, the vector D, we can have it as R, we have theta, and we can also have in the phi direction. But we have agreed, as mentioned by your friend just now, that the vector D will only be in the R direction, where the theta and phi, both of them can be simply equated to 0. So we only have a D as a dr of R. So we're going to use it still here. So we're going to have dr direction of R for your vector D. And the ds is the ds on this particular Gaussian surface. And we have agreed that the ds will be R squared sine theta, the theta, the phi direction of R as before. So we can proceed that this d dot ds will be dr of 4 pi R squared, where R is a radius of your Gaussian surface. Yeah. Whereas for the right-hand side, yeah, right-hand side, which is enclosed charge, the enclosed charge is equals to rho v dv, which is a charge inside the Gaussian. So we can have it as rho v integrations of my mistake, yeah. Okay, this will be R squared sine theta dr d theta d phi. Okay, you have to be very careful on this selection of radius R. Okay. If we proceed with the integrations, yeah, I think it's good if we can proceed with the integration first. So we're going to have integrations of R squared dr, integration of sine theta d theta, integrations of d phi. So phi, because we are dealing with the closed structure here. Okay, I think it's good if we can identify what is the location of your enclosed charge then here. Can I ask Ihsan Aulia Rahman, are you in? No, yeah. Taufan Surya Putra, are you in? Taufan Surya Putra? What happened to this guy? Yang Jianyu?
Yes, doctor.
Okay, thank you, Tesla. Can you please help me? If we base on this structure, the enclosed charge, what should be the position? I mean, what should be the range of radius for your enclosed charge for this case?
From 0 to R0.
R0, very good. Very good, Tesla, for your answer. So it means that your charge is only within 0 to R0, no charge elsewhere. It means that no charge from R0 to R, yeah?
Yes.
Thank you, Tesla. So you can switch off your mic there. Thank you very much. Yeah?
Okay. Thank
Okay,
you.
so for that, we can see that the range of integration of R will be from 0 to R0 only. 0 to R0 only. No charge from R0 to R. Yeah, that's why we cannot integrate R0 to R, because from R0 to R there is no charge. Yeah, charge is only within 0 to R0 only. So that's why the integration here will be from 0 to R0. Yeah, thank you, Tesla, for your answer. Very good. So theta will be from 0 to pi and phi from 0 to 2 pi, because we are dealing with a complete spherical structure. So for this, we're going to have the integration of rho v 4 over 3, yeah, 4 over 3 pi r naught power of 3. Okay, so that should be your enclosed charge. So now we can equate both left and right hand side equation. So we have dr 4 pi r squared equals to rho v 4 over 3 pi r naught power of 3. So we're going to have it as dr equals to rho v, 4 can be cancelled out, pi can be cancelled out. We're going to have 4 rho v over 3 r naught power of 3 divided by r power of 2. Yeah, r naught and r are two different things. Yeah, r naught is a constant, r is a variable. Yeah, r naught is a constant, r is a variable. So that should be your vector d, so your dr. And subsequently, we can write that the vector d will be dr of r, which is from this understanding before. So we can have it as dr of r. So we're going to have vector d as rho v r naught power of 3 over 3 r power of 2, direction of r coulombs per meter squared. Okay, so this is the vector d which has been calculated or which has been measured on this Gaussian surface with a red colored line here. Yeah, that's your vector d. Yeah, and the third steps, yeah, which is to find the E field based on this equation d of epsilon naught of E. So we can have the E field shall be d vector over epsilon naught, and we're going to have it as equals to rho v r naught power of 3 over, sorry, yeah, 3 epsilon naught r power of 2 in the direction of r volt per meter unit. Yeah, so that should be the E field equation. Rho v r naught power of 3 over 3 epsilon naught r power of 2 direction of r. So this is the E field which is measured here. Any point having a radius of r from your center of a sphere. Yeah, and this r here is only valid for a value of a radius bigger than r naught. So we have two distinct equations. The first one is for the d and e inside the sphere, where we have an equations before. Yeah, we have the r here. Yeah, we have the r value then. And this is second thing, a second part, which is the equation of d and e for any position, any point bigger than r naught. Okay, so hopefully by now we have you have understand how we can use the Gauss law in calculating the electric field intensity E for a given symmetrical problems charge structure. Is it okay with this example? Any questions?
Hello, doctor.
Yes.
Why we only consider the R component?
Okay, as I mentioned before in my earlier discussion of these questions, Imagine that we have a point charge, yeah? A point charge, a Q, for example. We have a grid before that. For the point charge, the D and the E is in the R direction. Am I right? The case of point charge, yeah? Okay, so the point charge, Q, we can see that if we increase the radius of R, increase the radius, yeah, we can have it to be look like this. Am I right? You have a charge here. This is a spherical, this is your
Yes.
spherical structure, which is produced or obtained from a point charge which has been increased in terms of the radius. So somehow, this direction of the D and E will be similar to the point charge problem just now, but the direction is still in the R direction.
Mm.
Okay then?
Okay.
All right, thank you very much. What's your name?
Raymond.
Oh, Raymond. Okay, thank you, Raymond. Okay, so that's the argument, yeah? So that's our assumption. We increase the radius of the point charge, we're going to achieve or going to obtain the volume charge structure. Okay, so remember, in using the Gauss law, you have to choose only one direction of the D. Yeah, for this particular case, whether you're going to choose the R, to choose the theta, or choose the phi. So that is why the Gauss law is only applicable for a symmetrical charge distribution. Because for a symmetrical charge distribution, the direction of your flux density D or E will only be in a single value or single direction. Okay, that's why the Gauss law can only be applied for a symmetrical charge distribution. Okay then? Okay, let us proceed in the second example here, which is for the case of cylindrical structure. Yeah, cylindrical structure. Okay. We have this case similar to what we have done before. Yeah, basically similar to what we have done before, in which we are having a cylinder. Yeah, that's our cylinder, which is assumed to be infinite in length. Yeah, this is infinite in length. We can assume this look like this. That's your cylindrical structure, which is having a density of rho v. Yeah, a density of rho v. The charge density is of rho v, and the radius is r naught. Okay, sorry. Yeah, radius is r naught. So that should be your given cylindrical structure. So you have to find again the D and E for inside and outside the cylinder. All right. So basically the idea should be same like what we did before for the case of spherical structure, but we have to do it now. So for the first case, which is for the inside, inside the cylindrical structure, we have to choose the radius of R, yeah, radius of R, which is less than R naught, yeah, less than R naught, in which R is a variable. Yeah, R is a variable. So let us proceed with the Gauss law. The first one is to use to sketch the Gaussian surface. Okay, so for cylindrical structure, as what we have learned before, your appropriate Gaussian surface should be a cylinder also. Yeah, so that should be your Gaussian surface, a cylinder. Sorry, yeah, not so nice, my drawing. Okay, so that should be your Gaussian surface, in which the Gaussian surface here is having a radius of R. I think it's good if I can use bigger dimension. Sorry, I think it's good if I can use bigger drawing for this. Yeah, it's easier for us to see then. Okay, so we have okay, that is your Gaussian. This is your cylindrical structure given. Okay, it is infinite in length. Okay, so that is your radius of R naught given, and the density is rho v, coulombs per meter cube, which is a volume charge distribution. Okay, the first case, which is for the inside. Yeah, for the inside region. The first one is to draw the Gaussian surface. So as I mentioned before, you have to use a cylindrical structure as a Gaussian surface here. Okay, that's a Gaussian. Okay. The Gaussian is chosen to be having a radius of r, and the length of the Gaussian, or the height of the Gaussian, is L. Okay. So you have to choose, you can see that for the inside region, you have variable of r, yeah, where r is less than r naught. Yeah, r is a variable, any point within the r naught radius, that should be the r. Okay, so you have sketch the Gaussian surface. Number two, you have to use the Gauss law. So d dot ds equals to the enclosed charge. Okay, for the left hand side, we have three surfaces. Yeah, the d dot ds consists of d dot ds for surface number 1, d dot ds for a surface number 2, and d dot ds for a surface number 3. Because for this Gaussian surface, the red colored structure here, we have three surfaces: number 1, number 2 down here, and number 3 of the curved surface. Yeah. Okay, so we can agree here that the direction of the flux density D for the case of a cylindrical structure here will be three directions. Initially, R, then we have a phi direction, and we can have Z direction, yeah, because we are using the cylindrical system of coordinate. But since we have infinite length of line charge, yeah, or infinite length of cylinder, we can assume only one direction. Yeah, one direction. So we can say that the direction will only in the R direction, where the phi and the Z can be equated to 0. Yeah. So we only have a single direction of R for this particular case. Yeah. So for surface number 1 and surface number 3, surface number 1 and surface number 2, the d dot ds for both surfaces can be equated to 0. Why? Because this is similar to our discussion before for the case of line charge distribution, in which for surface number 1 and surface number 2, the ds for both surfaces is in the direction of r. Sorry, direction of z, I apologize. Yeah? Z and negative z direction. Yeah, for surface number 1 is in positive z, for surface number 2 is in negative z. So when we proceed with the dot product of d dot ds, the value will be 0, yeah, because dot product between different vector will give us 0. So the d dot ds will remain only for the third surface, which is the curved surface. So end up we're going to have the integrations of dr direction of r, and the ds for the third surface will be r d phi dz direction of r. So this will give us dr and 2 pi r of L, which is the integration on this particular closed surface or red colored surface. You can have dr, 2 pi rl. Okay, for the enclosed charge here, yeah, the enclosed charge. So the enclosed charge, we base on this diagram, will be the charge enclosed by this particular Gaussian surface, the red colored surface. Yeah. So that will be written as integrations of rho v dv, which is the volume charge inside the Gaussian. So we can just write this as equals to rho v, and then we're going to have 2 pi, sorry, I apologize, my mistake. Okay, so the dv will be equals to r dr d phi dz. Yeah, and if you proceed further, we're going to have rho v pi r squared of L. That will give us the enclosed charge. Yeah, because your R, if I can make it clearer here, your integration of r dr, integrations of d phi, integrations of dz. Dz is from 0 to L because a Gaussian is having a length of L. Yeah, phi will be from 0 to 2 pi because this is a closed surface structure, so the phi will be maximum 0 to 2 pi, and your r, since your radius for the Gaussian is from 0 to r, so you're going to have r then. So when we proceed with the integration, you are going to have a pi r squared. of L. Yeah, pi r squared of L. Yeah. So we can equate now the left and right. Yeah. So we're going to use these two terms then. So we're going to have dr of 2 pi rl will be rho v pi r squared of L. So can we cancel out the L, the pi, and also 1 of R here. So end up we're going to have dr will be equals to rho v r divided by 2. Rho v, yeah, rho v r divided by 2, yeah. That should be your dr, yeah. Okay, and from here we can write that the d vector will be equals to dr direction of r. So that will give us rho v r direction of 2 in the direction of r coulombs per meter squared unit. So that should be your vector of d. Okay, so this vector of d is measured on this particular surface of Gaussian. Yeah. Okay, so that should be the second step. We have obtained the d successfully. And finally, the third step is to use to find the E field, where d equals to epsilon of E. Sorry, my mistake then again. Sorry for that. So the third step is d equals to epsilon of E. So we're going to have the E field will be d over epsilon naught. I'm going to have rho v r over 2 epsilon naught direction of r volt per meter. Yeah, because the d that we obtained previously is rho v r divided by 2. So that should be the equation of E field measured or calculated on any point. If I can sketch again, yeah, that is your given structure. So your Gaussian is inside here. Yeah, your Gaussian is here. Okay, having a radius of r. Okay, this is given r naught as your structure initially, r naught. So r is a radius of the Gaussian. So the equation here is only valid on this particular Gaussian surface in which any point having a radius of r. Yeah, any point having a radius of r, in which r here is a variable in which r must be less than r naught. So this equation of E field is only valid for any point of r less than r naught. Yeah, less than r naught. Okay then, is that clear? Somehow the method is similar to what we have done before for the case of volume charge of a sphere. Yeah, it's similar. Okay then. So do I need to do I need to proceed with the outside sphere? So can you do it on your own for the outside region of the sphere?
Doctor, I think I missed out something. What is the d bar?
The d bar. This d bar, is it?
Yeah.
Oh, okay. This is your electric flux density. Electric flux density.
Oh.
Yeah, you have to refer to the earlier part of this lecture number 6. So we have discussed about the flux density there. Yeah.
Okay, thank you, Doctor.
Okay, welcome. Okay, any questions
Sir,
still?
Doctor.
Yes.
I still confused how to determine the direction of the flux density.
The direction of flux density, yeah. Okay, so for this particular case of a cylindrical structure, we have options. The d will be r direction, will be theta direction, and phi direction, phi, and z direction. Am I right?
Yes.
Okay, so similarly to our previous discussion for a spherical structure, we can assume that this particular cylindrical structure is originated from a line charge. For a line charge, what is the density, what is the direction of the flux density?
Horizontal?
From these three, whether it's r, whether it's phi or z, for the case of infinite length of line charge. What should be the direction of the d? Rehan?
R?
Good. It's only r, right? It's only
yeah.
r. Okay, because you know that the direction of the field will be in the r direction. Okay, like this, yeah, that should be the direction of the phi or the E field. Okay, in which the theta and phi is the phi and z can be cancelled out due to this argument. So we can assume that this particular cylindrical charge distribution is originated from this line charge, in which if we increase the radius of this line charge, we are going to produce this kind of charge distribution. Okay, so when we increase the radius of line charge, we are going to have this charge distribution structure. So due to this, again, we can assume that for volume charge, for this cylindrical structure, we'll only be having a single direction of unit vector of r for the flux density. Is that clear on my explanation?
Okay,
Okay.
I understand.
Thank you, Mehan. Thank you very much. Okay, again, my question is it okay for you to proceed on your own for the region of R bigger than R0 to find the D and E? R bigger than R0, which is outside the cylindrical structure. Is it okay for you to do it on your own? Taufan Surya Putra? He's the first student to get into my Google Meet this morning. He's missing now. What happened to him? He's having breakfast? Iftiak Hossain, are you in my class today? Still, he's not in, yeah? He has been missing my class for the past 3 weeks. Okay, so I think he's in big problems now, yeah? Because the test one is around the corner within this 2 or 3 weeks time. Ah, okay. Right, so never mind. I think you can do it on your own to find the D and E for this region. So you can try to adopt the method that we have seen before for the case of spherical charge distribution. Okay, so please try on your own. If you have any problem with that, you can always consult me, yeah, for any questions related to this issue. Thank you very much. Okay, let us proceed now with the example number 3. We are given these problems where we have the D vector, the flux density D is given to be R of 3, R divided by 3 direction of R in free space. Yeah. The question is find the E field at R equals to 0.2. That's the first one. Number B, find the total charge within a sphere of 0.3 meters. And C, find the total electric flux leaving the sphere of R of 0.3 meters. Okay. Yeah, so I think this is a very straightforward problems, which is just to make you understand related to the Gauss law and flux concept. Okay, let us proceed then. Okay, given here that the flux density D is given in a free space environment, find the E. So this is to be based on the equations that we have seen before, relationship between the D and E. So D will be equals to epsilon naught of E field. And from this relationship, we can say that the E field the E field will be equals to D vector over the epsilon naught. So we're going to have it as R over 3 epsilon naught direction of R volt per meter unit. Okay, so at R equals to 0.2 meters, we can say that the E field will be simply equals to 0.2 divided by 3 epsilon naught direction of R volt per meter. Yeah, it's just simply like that. It's just to show you, just to see your, to evaluate your understanding on relationship between the D and the E. Okay, part B, the question is to find the total charge within the sphere of R 0.2 meters. Yeah, find the total charge within the sphere of R 0.2 meters. Okay, so we are given the D. Yeah, so we can say that if we have a sphere of 0.2 meters, okay, this is for part B of the questions. We have a sphere, okay, and the sphere is having a radius of 0.2 meters, okay. We need to find the total charge within this particular sphere, in which we are given that the vector D is given by these equations, yeah? Okay, so these need to be based on the Gauss law equation where we have the d dot ds equals to enclosed charge. So the total charge within the sphere is based on the right hand side, which is the enclosed charge. Yeah, so which means that if we have this sphere of radius 0.2 meters, the enclosed charge is what should be the charge that is located inside this particular sphere of 0.2 meters. So we can find the enclosed charge by evaluating the left hand side, which is the closed surface integration of d dot ds, in which we need to evaluate this integration on the surface of a sphere. Yeah, so this is the Gauss law indirectly. Yeah. Okay, so we can find the charge within the sphere by simply evaluating the d dot ds. So for that, we can say that the total charge inside the sphere will be simply closed surface integration of the d dot ds, in which the d is given by r over 3, direction of r, and the ds vector, which is on this particular surface of your sphere, will be simply r squared sine theta d theta d phi, direction of r. Okay, so we can proceed with the integrations then, where we have the charge will be integrations of we have 1 over 3 outside here. We have r power of 3 dr, integration of sine theta d theta, integrations of d phi. So we know that this particular sphere is having a radius of 0.2. So simply we integrate from 0 to 0.2. Theta is a full sphere, so 0 to pi, and phi will be 0 to 2 pi. So proceed with this, going to have r power of 4 divided by 4 from 0 to 0.2. And then we have, that should be 2, that should be pi. Going to have 4 pi, eh? We have to have 4 pi divided by 3. Okay then? Oh, sorry, my mistake. There is no, sorry, it's my mistake. I thought it's a volume. Sorry, it's my mistake. Sorry for this. Yeah, I need to correct it. Okay. Right. So basically, this is the integration. There is no R integration. So we're going to have the charge enclosed, or the enclosed charge will be R power of 3 divided by 3. Okay, so that should be integrations of sine theta, d theta, integrations of d phi, 0 to 2 pi, 0 to pi. So we just substitute the value of r of 0.2 meters straight away. Okay, so we're going to have it as a 0.2 power of 3 divided by 3, and that should be equals to 4 pi. Okay. Okay then.
Doctor, for
Yeah.
the unit nano given in the question will not affect the calculation, right?
The unit of nanocoulomb. Okay, so based on this, your charge will be in nanocoulomb. Yeah, your charge will be in nanocoulomb. Yeah, because we know that the vector D should be in nanocoulomb. Sorry, in this particular case, nanocoulomb per meter squared, and your ds, this ds is in meter squared. So we multiply with the two, going to have the answer will be in nanocoulomb. So that should be your charge amount in nanocoulomb unit. So that should be the charge amount in nanocoulomb.
And how about the unit for A? For A, the electric field will be
Okay, for this
what
particular
per
case,
meter?
correct. So it should be in nanovolt per meter. Thank you. Nanovolt per meter. Yeah.
Oh, okay. Thanks.
Okay, thank you. Okay, then I think it's a straightforward question. Yeah, in which this example is to show you is to test your understanding whether you understand the relationship between the flux and the charge. Yeah, the flux and the charge. So as I mentioned before in earlier part of lecture 6, the charge and the flux are interrelated. Yeah, the flux and the charge are the same basically. Yeah. Okay, so for part C of the question, I think this is similar to part B. Yeah, both are interrelated, yeah, because for part B is to find the total charge within the sphere, and C is to find the total flux leaving the sphere. So basically both are the same, except that radius is now changed from 0.2 to 0.3. Okay, so you have to use the same equation, the same integration. I mean, you have the same equation, you just change the R to 0.3 for the part C, yeah? Okay, so I think I made it clear to you on these issues of relationship between the charge and also the flux, yeah? Any question for this example number 3? No? Okay, then if there's no questions, I think we can proceed to the example number 4. All right. Example number 4, we are dealing with a cylindrical surface in which in this particular problems we are given 3 different radius or 3 different surfaces. Each is having a radius of 1 cm, 2 cm and 3 cm respectively. So we have three surfaces, yeah? 3 surfaces having this radius 1, 2 and 3 centimeters. Each of them carry this surface charge distribution 20 nanocoulomb per meter squared, negative 8 nanocoulomb per meter squared, and 5 nanocoulomb per meter squared. Okay, then. The first question is, how much electric flux passes through the closed surface 5 cm z from 0 to 1 meter? Okay, that's the first question. I think we can proceed with the first question first. Yeah. Let us sketch this diagram, these surfaces. So we have 3 surfaces, number 1, number 2, and number 3. Okay, so these are 3 surfaces, right? All right. Hopefully you can distinguish these 3 surfaces here. So this is 1 cm radius, that is a 2 cm radius, and then we have a 3 cm radius. Yeah, so these are 3 surfaces of cylinder in which each of them is having different charge distribution. So remember, yeah, the charge distribution is nanocoulomb per meter squared, means that your charge is only on the surface of your cylinder. So for this, it is 5 nanocoulomb per meter squared, which is on the surface only. Also here on the surface, which is negative 8 nanocoulomb per meter squared. And finally, on the inner surface here, the charge distribution is 20 nanocoulomb per meter squared. Okay, I just want to remind you again that the charge is only, the charges are all located on the surface of your cylinder. No charge inside the cylinder. So you have to be very careful on this. Yeah? So when you are given the problems, first thing first, you have to understand the problems clearly. Okay. So previously, our example are dedicated towards a volume charge. So now the problems has been shifted to a case of a surface charge distribution. So we have these surface charge, 3 surface charges, yeah, three surfaces, 1 cm, 2 cm, and 3 cm with respective surface charge distribution. The first question is, how much electric flux passes through the closed surface of R 5 cm and height from 0 to 1 meter? Okay, so 5 cm radius, where should it be located? 5 cm radius. So because your radius is only up to 3, so basically your radius, I mean your structure of interest here should be located outside, yeah? It should be located outside your structure, yeah? So if I can sketch it for you, your structure somehow should be located here. Okay, so I draw it in a dotted structure, yeah, dotted structure. Okay, that's your surface, dotted surface. Okay, and the radius for it is equals to 5 centimeter. Okay, so that is your structure, your closed surface structure, yeah. And the height of it is equals to 1 meter, yeah, 1 meter, right? So that is your surface, the closed surface, given to be a 5 centimeter radius, and the height is from 0 to 1 meter. The question is, find the flux passes through this closed surface structure. So how you want to find the flux leaving the surface? Okay, so this is based on the Gauss law still, which is similar to our previous discussion, yeah? This example that we did here, in which if you want to find the flux leaving, yeah, flux leaving this particular surface, what you can do, you can find the charge inside that particular closed surface, because the flux and the charge are equal, yeah, flux and charge are equal. So you can find the flux leaving this closed surface by simply calculating the charge inside the surface. So that should be the answer. So you need to find the charge then. So knowing that in your closed surface, there are 3 surfaces. So your charge, total charge, shall be a contribution from 3 surfaces, which is rho s ds for surface number 1, rho s ds for a surface number 2, plus rho s ds for your surface number 3. Okay, assume that surface number 1 is 1 cm, surface number 2 is 2 cm cylinder, and surface number 3 is 3 cm cylinders. Okay, yeah? Okay, let us proceed with surface number 1 first. Yeah, so for surface number 1, rho s ds for surface number 1, we can have it as integration. So for surface number 1, the density is 20 nanocoulomb per meter squared. Okay, all right, and the ds will be the charge on your curved surface, yeah. So that should be r squared sine theta d theta d phi, and we can just simply write it as 20 nano multiply with this area, which is 4 pi r squared. Okay, 4 pi r squared, just like that, yeah. Okay, so I'm going to have it as a 20 nano times 4 pi, and r will be 0.01 meter, yeah, squared, and that should be the answer for the charge amount in for surface number 1 in nanocoulomb. Yeah, for surface number 1. Okay, do the same thing for surface number 2. Yeah, for surface number 2, I have to use it to do it here. So rho s ds for surface number 2. So we're going to have it as 5 nano, integration of 5 nanocoulomb. And your ds will be again r squared sine theta d theta d phi, and we're going to have it as 5 nano 4 pi, and r will be 0.02 squared, and you're going to have the answer in nanocoulomb. Okay, so do the same thing for surface number 3, and you need to add them together. So that will give you the total charge, which is enclosed by this particular closed surface, and that should be equal to the flux passes through the closed surface. So is that understood for this example? Okay, so the motivation, I mean, the basic ideas is to find the flux leaving the surface, you must first find the charge inside the surface. So that will be your flux amount, yeah? Because flux and charge are the same thing. Is that answer the questions for part A? Any question for that? Sorry, I think I made a mistake still here. I see. Sorry for this. I made a mistake. This is not a sphere. This is a cylindrical structure. How can I make this kind of mistakes? Yeah. Sorry for this. It's my mistake. Sorry, guys. It's my mistake then. Sorry for that. This is a cylindrical structure, so you cannot use the ds as this. Okay, so that should be r d phi dz supposedly, yeah, supposedly. So when you proceed with the integration, you're going to have 2 pi rl. Your L is given to be 1 meter, R is a radius for your structure, so it should be 20 nano, and your 2 pi L should be 2 pi, R is 0.01 meter, and L is 1 meter. Okay, so you're going to have the answer in nanocoulomb. Okay, the same thing is applied for surface number 2, where you have the integrations of 5 nano, coulombs per meter squared. And your ds will be 2 pi, sorry, r d phi dz. Okay, and then we're going to have it as 5 nano, and that will be 2 pi rl. It should be 5 nano and 2 pi times 0.02 times L. So L is 1, yeah? L is 1 meter. Okay, so you're going to have your charge amount in nanocoulomb. This is the charge amount at surface number 2, which is radius of 2. Okay, do the same thing for surface number 3. Sorry for my mistake. Yeah, because what I did just now is I'm using a spherical surface, so that's my mistake. Yeah. Okay. Any question then for this part A of the question? Chai Bing Cheng, are you in my class?
Yes, doctor.
Okay. You have any question, Chai Bing Cheng, for part A?
I mean, why the surface 2 using the 5 nano? It should be negative 8 nano coulomb.
Okay, thank you. Thank you. It's my mistake. Thank you very much. Okay, it should be negative 8. It's my mistake, yeah? So negative 8, thank you. All right. Thank you, Bincheng, for your correction. It's good, yeah? So it's negative 8 now instead of 5.
Welcome.
Thank you. Okay then. So I think we can proceed with part B of the questions, yeah? Part B, okay. Okay. So part B basically is to find D at this position, which is 1, 2, and 3 centimeters. Okay, so basically you need to know what is the actual radius for the point of P. Okay, yeah. So if we base on that, let's use a Cartesian system of coordinate x, y, and z. Yeah. So x should be 1, or y should be 2, and z should be 3. Yeah. So that should be your position. Okay, and the radius. What should be the radius for this? If you're using a cylindrical structure, so because this is based on cylindrical surfaces, so what should be the radius for this particular point of 1, 2, and 3 centimeters? Can I ask Teo Peting? Are you in my class? Hello, Teo Peting? Okay, what happened to Teo Peting? Wong Li Hong, are you in my class? Oh, what happened to these students? Yeah.
Doctor.
Yeah. Who is that? Teo Peting?
Yes,
Hello.
doctor. Sorry.
Okay. What happened to you?
I pressed the wrong button.
Oh, okay, never mind. Okay, please help me regarding this point of P. Can you please help me? What is the radius for this point of P?
The square root of 1 square plus 2 square plus 3 square.
That should be this radius, right? If you use that method, that should be 1 plus 2 plus 3.
Yes.
But this is for the case of spherical. But the one that we have here is for cylindrical.
Oh.
So what should be the surface? What should be the radius then?
2.
So your radius should be this radius, right? Which should be square root of 1 squared plus 2 squared only. Am I right, Peting?
Yes.
Yeah, so it should be square root of 5. Thank you, Peting.
Okay.
Thank you for your help. Next time, please press the correct button, yeah? Okay, let us proceed now to find the D at this position of a radius set of 5. So we have agreed that the radius for the point of P will be here, which is set of 5. So the set of 5 basically is located between 2 and 3, right? This point of set of 5 is located between 2 and 3. yeah, between 2 and 3. So if you base on your cylindrical surface just now, yeah, so let me sketch it. Okay. Okay, so that is your structure. Okay. Right, so that's 1, that's 2, and that is 3. Yeah, 1, 2, and 3. Okay, so your set of 5 just now, yeah, we have agreed that the radius of R will be set of 5. Yeah, will be set of 5, sorry, set of 5. So set of 5 located somewhere at this particular point here, yeah, between 2 and 3. So in order for us to find the flux D at this particular point of P, what you have to do is that you have to find the flux density D between the point of 2 and 3 cm. Yeah, between the point of 2 and 3 cm. That should be the point of interest. So what you have to do now is that you have to find the D here within this point, okay, in which your Gaussian surface should be based on this region. Yeah. So when you apply the Gaussian surface, you're going to have the D dot ds should be equals to the enclosed charge. Okay, and your Gaussian will be, if I can say it for you, sorry for that, yeah. That should be a Gaussian, yeah. Sorry for this. Okay, that should be a Gaussian surface between 2 and 3, and we assume it to be having a distance or height of L, for instance. Okay, so what you have to do now is that you have to find out what should be the value of D at this particular point, yeah, at this particular point, between this particular region, find the vector of D, and from this point of D, from this value of D that you have obtained between the 2 and 3 region, 2 and 3 radius, you can obtain this equation for the D vectors, and subsequently to find the value of D at this point of P, we just substitute the value of R to be equals to set of 5. Okay, so since we don't have not much time, it's already 9:50. So we are going to continue these topics, this lecture, this coming Thursday. Okay, so please try to find out the value of D vector for this region between 2 and 3. Okay, and afterwards, once you have it, we just substitute the value of R to be set of 5, then only you can get the value of D at this point of P. Okay, so please try all this on your own to find a vector of D for region between 2 and 3 radius. Okay, so I'm going to stop now. I'm going to meet again this Thursday for more lectures on Gauss Law, and hopefully we can finish chapter 3 on Gauss Law by this Thursday class. Yeah, right. With that, I end the class today now. Yeah, thank you very much for your cooperation and your response. I'm going to meet again this Thursday. Yeah. Okay. Thank you. Bye bye.